Okay, so this video is going to just do a real quick, easy example, and then we're also going to look at the relationship of IC1 and IC2 as it changes with the differential voltage, and look at a graph that I think will help kind of explain this here. So we don't really need the circuit drawn here, but it is the standard differential amplifier circuit. And so we're basically saying that we have an IQ of 1 milliamp and we're supposed to compute the value of VD, my differential voltage, so that IC2 is equal to 0.99 IQ. Well, clearly that just means that IC2 is going to be 0.99 milliamps. So nothing really too surprising by that. And this is really just a quick equation, plug and chug. There's not much beyond it. And what we have here is IC2, remember, is equal to IQ over 1 plus e to the negative VD over VT for IC2. I'm sorry, I forgot that. It's not negative, it's positive for IC2. I already messed the equation up there. Positive VD over VT. And so I'm just going to actually quickly solve this just algebraically for VD. So you'd have 1 plus e to the VD over VT is equal to IQ divided by IC2. And so you'd have e to the VD over VT is equal to IQ over IC2 minus 1. Take the natural log of both sides, so you have VD over VT is the natural log of IQ over IC2 minus 1, and then VD would be VT natural log of IQ over IC2 minus 1. Now if we do this computation here, we'd have VD, of course, is equal to 0.026 volts times the natural log of 1 milliamp divided by 0.99 milliamps minus 1. And keeping track of negatives and everything, I wind up with negative 119.5 millivolts is what I would be setting VD at. Now, what I want to point out here with this example here is notice that the difference in this voltage is still pretty small. It's 0.2 volts is the difference, because remember VD is defined as V1 minus V2. So it's not saying that V1 or V2 is 0.2 volts. It's saying the difference between them is 0.2 volts. And a difference of 0.2 volts between them means that IC2 is 0.99 milliamps, which means almost all the current's going through IC2. In other words, IC1 is practically zero, so it's almost like transistor 1's off at this point. And we can see here, even though this question wasn't asking for it, is if we do use a VD of negative 119.5 millivolts is, well, what would IC1 be? Now, clearly, IQ is equal to IC1 plus IC2, which just gives us that IC1 is 0.01 milliamps. I mean, we know that, but I want to use my equation here that we had developed in the previous lesson, that this is equal to IQ over 1 plus e to the negative VD over VT. And so if we use that equation here, we'd get 1 milliamp divided by 1 plus e to the negative let me be careful here, negative 0.1995, because I converted it to volts, divided by 0.026. And if I do that computation, I get 0.465 microamps. I'm not sorry, 464 microamps. Which, if we convert that, we would get 0.000464 milliamps. And you might say, I'm not getting the 0.01 milliamps like I said I should. Yeah, I'm not. And even if I rounded, I wouldn't. What's going on here, again, is we've made some kind of simplifying assumptions here to get this. Plus, first off, I didn't round. I rounded this answer here, and anytime you round and you're dealing with exponentials, that's going to introduce a huge amount of error. Because why? Well, exponentials, remember, what kind of curve do they have? They have a curve that looks like this. So anytime you round, you know, if this is the actual answer right here, but if you round it to right here, we can see we have a very big change in there. So, but we're still in the, quote, orders of magnitude, in the sense that, yeah, we're getting something that's, you know, a very small current, you know, here that, you know, we shouldn't be getting more than and actually I think I have that conversion wrong there. No, that's right. What I have wrong here is that this should not be 0.01 milliamps, should it? No, that is. Let me see, what do I have wrong here a second? My mistake here is that I can't convert here. This would be 0.464 milliamps. Apologize about that. Which again seems like we're 40 times bigger, but again, the reason we're getting that here is because of this exponential. So what's the rule of thumb that we should do here? Well, the rule of thumb that we should do is, you know, and we also have a further assumption, we're neglecting base currents, but that's fine, is that once we find this here, if we're trying to find what IC1 would be, it would be better to use the fact that IQ is equal to IC1 plus IC2 as opposed to doing the VD, because again, small changes in this exponential will have significant impact on the answer. Alright, but what I want to further discuss here is, let's look at a graph here. And this will become a little bit clearer than the conversation we were having with IC1 and IC2 just above there with our computation that didn't work out quite as nicely as I was hoping it would. And I am sorry. I did have this right here to begin with. And this is going to be, let me redo this here. I'm just not using my calculator correctly. So I'm going to pause this and do this computation again. Because when I do this computation again, finally, what I actually wind up with is 0.465 microamps is what the current is, not 465, 0.465 microamps for IC1. And we know that IC1 should be 0.01 milliamps, which would be 10 microamps. And we're definitely getting something wrong here, but again, it's this idea of this exponential here, because this is becoming a big number here, and as soon as this becomes a big number, we're going to have some issues with the exponential and any kind of rounding that we've done. All right, get back to the graph here. So this here is going to be VD. I'll go ahead and just label it here. This is going to be my differential voltage. And we're going to have 0 volts. Now, if VD is 0 volts, a 0 volt VD is actually giving me a common mode current. So if we think about it here, if we have this being 1 milliamp, then at 0 volts, we know that the current just divides equally between them. And then what we're going to do here is we're going to get here and let me draw this curve a little bit better. That looks too much like a straight line. Although it is kind of looks like a straight line, but so this might be, for instance, this would be IC1. And this would be IC2. And so what we can see here is that, well, when we're up in this 0.99 milliamp range here, because what we're looking at is something like right here. This is where the problem we were examining. And so we're down at these small currents here. And again, because these currents are actually getting close to 0, any small difference in this voltage is going to cause a big difference in the current there. But this is the idea what's going on here, because if we have no voltage applied, and sorry, I shouldn't say no voltage. If the voltage difference is 0, we have 1 milliamp going through each other. But as we get a more positive VD, so remember VD is equal to VB1 minus VB2. As this becomes positive, transistor 1 is getting turned on and basically having all the current going through transistor 1. And then as VD is negative, essentially all the current is getting through transistor 2. And then there's this small region right here, which this region in here, let me see how I want to box this. This region right here is, this is where the transconductance comes from. Because it's my slope. Now, and we call this area, it is kind of a linear region. Now, you might say, why did we only look at this slope here? Well, we can see that the blue curve is going to have the same slope except that it's negative, right? So we only really need to think of one of the slopes here. Because even though we have two different transistors, in essence, they have the same transconductance at any differential input. It's just a matter of one being positive and one being negative. All right. But we're going to move on with some other things here in the next lesson.